The universe, vast beyond our comprehension, contains billions of galaxies, each with billions of stars and likely even more planets. Given the sheer number of potential habitats for life, the Fermi Paradox poses a fascinating and perplexing question. Why, with so many opportunities for life to develop, haven't we found any sign of intelligent extraterrestrial civilizations? Before we proceed with detailing the chapters, it's important for you to understand two terms, as these will be used throughout the narration: the Great Filter and Fermi Paradox. The Great Filter is a theoretical concept used to explain why, despite the vastness of the universe, we have not yet encountered extraterrestrial civilizations. It suggests that there is some incredibly difficult and rare barrier, referred to as the filter, that prevents civilizations from reaching an advanced stage of development. This filter could exist at any point in the evolution of life, from the emergence of life itself to the development of intelligence, to the ability to communicate across interstellar distances. If the Great Filter is ahead of us, it means that humanity may face challenges in the future that could prevent us from becoming an interstellar civilization. If it is behind us, it means that we may have already passed the most difficult obstacles and are uniquely positioned to thrive and explore the stars. The Fermi Paradox. The Fermi Paradox is the apparent contradiction between the high probability of the existence of extraterrestrial civilizations and the complete lack of evidence for or contact with such civilizations. Now that you have the context, let's dive deeper into the concepts. Chapter 1: The Scale of the Universe and the Probability of Life. The vastness of space, a universe full of possibilities. When we look up at the night sky, we see only a tiny fraction of what exists beyond Earth. Our planet orbits a single star in a galaxy that contains between 100 billion and 400 billion stars. That galaxy, the Milky Way, is just one among an estimated 2 trillion galaxies in the observable universe. The sheer vastness of space is difficult to comprehend, but it is important to grasp the scale before we discuss why the absence of extraterrestrial civilizations is so puzzling. Astronomers estimate that there are at least 100 billion trillion stars in the observable universe. If even a tiny fraction of these stars have planets, and an even smaller fraction of those planets are capable of supporting life, we should expect the universe to be teeming with civilizations. Yet despite all our efforts, we see no undeniable evidence of alien intelligence. The famous physicist Enrico Fermi posed this paradox in the 1950s. During a casual conversation about extraterrestrial life, he asked a simple yet profound question: where is everybody? This question, now known as the Fermi Paradox, highlights a major contradiction. Given the age and vastness of the universe, intelligent life should have appeared and spread across galaxies. Yet we see no sign of them. No radio signals, no spacecraft, no interstellar megastructures. The absence of evidence raises the possibility that some great obstacle, a great filter, is preventing civilizations from advancing, or perhaps even emerging at all. The Drake equation, estimating the number of civilizations. In 1961, the astronomer Frank Drake developed a mathematical formula to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way. This formula, now called the Drake equation, breaks the problem into specific factors. First, we consider how many stars form in our galaxy each year. Then we estimate what fraction of those stars have planets. Among those planets, how many might be capable of supporting life. Next, we ask what fraction of those planets actually develop life, and what percentage of that life becomes intelligent. Finally, we determine how many intelligent civilizations develop the technology to communicate across space and how long they remain active. Each factor determines the likelihood of intelligent life forming and surviving long enough to communicate with others. What the equation tells us. Using optimistic estimates, the formula suggests that there could be thousands or even millions of advanced civilizations in our galaxy alone. However, our searches, including decades of listening for alien radio signals, have come up empty. So, what's the problem? Are the numbers wrong? Are we using faulty assumptions, or is there something stopping civilizations from reaching an interstellar level? This is where the idea of the Great Filter becomes crucial. Statistical certainty versus observational silence. One of the greatest paradoxes in science is that mathematical models suggest life should be common, yet observational data shows silence. Scientists call this the Great Silence, a universe that should be filled with intelligent signals, yet remains eerily quiet. The age of the universe. The Milky Way alone is about 13.6 billion years old, nearly as old as the universe itself. Earth formed about 4.5 billion years ago, meaning there were over 9 billion years for potentially habitable planets to form before us. If intelligent life evolved elsewhere, even just 1 million years before us, their civilization should be vastly more advanced than ours. They could have colonized the galaxy many times over. And yet we find no Dyson spheres, hypothetical megastructures built around stars to harness their energy. We see no artificial signals beaming through space. We detect no intergalactic spacecraft traveling between star systems. Von Neumann probes. Why haven't we been visited? One argument in favor of extraterrestrial life suggests that instead of traveling themselves, advanced civilizations might send self-replicating machines, known as von Neumann probes, to explore the galaxy. These probes could land on new planets, gather resources, and build copies of themselves, spreading exponentially. Given the age of the galaxy, such probes could have reached every solar system millions of years ago. But so far, there is no evidence that such probes have ever arrived here. Possible explanations for the silence. If we accept that intelligent civilizations should exist, then their absence suggests one of several possibilities. One possibility is that life is much rarer than we think. Perhaps the conditions for life to emerge are so specific that it has only happened once, or very few times in the universe. Another explanation is that complex life is extremely rare. Maybe microbial life is common, but the leap to intelligent, technological life is exceedingly difficult. A more concerning possibility is that intelligent civilizations self-destruct before they can spread beyond their home planets. Perhaps civilizations advance to a certain point before destroying themselves through war, environmental collapse, or uncontrolled technology. The universe itself may also be far more dangerous than we realize. There could be external threats, such as gamma-ray bursts, supernova, or even hostile alien species that wipe out civilizations before they can expand. Some theorists suggest that aliens are deliberately staying silent. According to this idea, civilizations may fear revealing their presence, avoiding potential threats from more advanced or hostile species. Each of these possibilities will be explored in depth in the coming chapters. A universe of possibilities, yet no answers. As we stand on the precipice of a new space age, humanity is still searching for answers. With new telescopes scanning the skies, artificial intelligence sifting through radio signals and interstellar probes pushing further into the unknown, we may soon find clues that help resolve this paradox. But for now, the great silence remains unbroken. Chapter 2. The origins of life. Is it common or incredibly rare? The cosmic conditions for life. Before we can determine whether life is common or rare, we need to understand the precise conditions that allow it to emerge. Life as we know it depends on a delicate balance of factors, from the right temperature range to the presence of key chemical elements. Earth, our only known example of a life-bearing planet, orbits a stable star in a habitable zone, a region where liquid water can exist. Our planet is rich in carbon, oxygen, nitrogen, and hydrogen, the essential building blocks of life. It has an atmosphere that protects against harmful radiation, plate tectonics that recycle nutrients, and a magnetic field that shields it from solar winds. If life arises easily wherever these conditions exist, then the universe should be filled with biological diversity. But if life requires an extremely rare set of coincidences, then intelligent civilizations may be exceptionally scarce or even unique to Earth. Abiogenesis, the first step in life's journey. The origin of life, known as abiogenesis, refers to the process by which simple molecules transition into self-replicating systems capable of evolution. Scientists believe that this occurred on Earth more than 3.5 billion years ago. There are several competing theories about how abiogenesis happened. One idea is that life began in deep-sea hydrothermal vents. These vents release mineral-rich water heated by the Earth's interior, creating a warm, energy-rich environment where primitive organic molecules could have formed. Another theory suggests that life originated in shallow ponds or lakes, where water cycles and UV radiation from the sun could have helped complex molecules form and link together. A more controversial hypothesis is that life came from space. This idea, known as panspermia, proposes that microbial life might have arrived on Earth aboard asteroids or comets, having formed elsewhere in the cosmos. Despite extensive research, scientists have not yet been able to recreate the exact moment when non-living chemistry transitioned into self-replicating biology. If this step is extraordinarily difficult, it could mean that life is incredibly rare. In that case, the great filter might lie right here, at the very first stage of life's emergence. The role of water in life's formation. Water is often called the universal solvent because it dissolves many different types of molecules, allowing complex chemical reactions to take place. This is why scientists prioritize the search for liquid water when looking for life beyond Earth. Mars, for example, once had vast oceans and rivers. If microbial life ever existed there, it might still be hidden beneath the surface, where liquid water is thought to exist. Saturn's moon Enceladus and Jupiter's moon Europa both have vast underground oceans beneath their icy crusts. These moons have active geysers that release water vapor into space, suggesting the possibility of hydrothermal vents beneath their oceans, similar to those on early Earth. The presence of water, however, is not enough to guarantee life. It is possible that while many planets have liquid water, they may lack the other crucial conditions needed for life to emerge. The Miller-Urey experiment, simulating early Earth. In 1953, scientists Stanley Miller and Harold Urey conducted a groundbreaking experiment to test how life's building blocks could have formed on early Earth. They created a sealed system containing water, methane, ammonia, and hydrogen, gases believed to have been present in Earth's early atmosphere. Then they exposed this mixture to electrical sparks simulating lightning storms. After a few days, they found that simple amino acids, the fundamental components of proteins, had formed. This was a major breakthrough, showing that the basic ingredients of life could emerge through natural chemical processes. However, while amino acids are essential for life, they are not life itself. The jump from simple molecules to self-replicating systems remains one of the biggest mysteries in science. The RNA world hypothesis, the first genetic code. One of the leading theories about the first living systems is called the RNA world hypothesis. It suggests that before DNA and proteins existed, life may have begun with RNA, a simpler molecule capable of both storing genetic information and catalyzing chemical reactions. Modern cells use DNA as a blueprint and proteins to carry out functions, but RNA can act as both a genetic carrier and a chemical catalyst. If early Earth had pools of self-replicating RNA molecules, natural selection could have favored those that became more stable and efficient over time. Eventually, these primitive molecules could have given rise to more complex life forms. While this theory is promising, scientists have yet to fully explain how RNA itself first formed in a natural setting. If the creation of self-replicating RNA is an extremely rare event, then the great filter may lie at this stage. How many planets could host life? The discovery of thousands of exoplanets, planets orbiting stars outside our solar system, has revolutionized our understanding of how common habitable worlds may be. Astronomers estimate that the Milky Way alone has at least 100 billion planets, and a significant fraction of them could exist in the habitable zones of their stars. If life is common, then simple organisms should have appeared on at least some of these worlds. However, finding life is not easy. Most of these exoplanets are located dozens or even hundreds of light years away, making direct observation extremely challenging. Scientists rely on indirect methods, such as studying atmospheric compositions for signs of biological activity, but so far, no definitive evidence has been found. The rare Earth hypothesis: is life uniquely uncommon? One argument against the idea that life is common is known as the rare Earth hypothesis. This theory suggests that Earth is not just another typical planet, but an exceptionally rare and fortunate one. Several unique factors make Earth particularly suited for life. A large moon stabilizes Earth's tilt, preventing extreme climate fluctuations. Plate tectonics recycle nutrients and help regulate the planet's climate. Earth has a magnetic field that protects against harmful radiation. The presence of Jupiter, a massive planet, helps shield Earth from frequent asteroid impacts. If these conditions are extremely rare, then the emergence of life may be just as rare. In that case, the Great Filter may already be behind us. Life itself might be the hardest step, and intelligent civilizations could be few and far between. Could we be the first? Another possibility is that life does emerge frequently, but intelligent civilizations take a long time to develop. If Earth is among the first planets to host a technologically advanced species, then we would not yet see evidence of others. This idea, known as the firstborn hypothesis, suggests that the universe is still in an early stage of civilization development. Perhaps other intelligent life forms will arise millions or even billions of years after us. A silent universe, for now. As we continue searching for extraterrestrial life, we must consider the possibility that the Great Filter lies at the very beginning. If abiogenesis is incredibly rare, then life may be an anomaly rather than an expectation. If this is the case, then we may be utterly alone in the vast cosmic ocean, with no one else to talk to, not because civilizations destroy themselves, but because they never form in the first place. Chapter 3, From Simple Life to Intelligence: Is Evolution a Bottleneck? The journey from microbes to minds. Even if life emerges frequently in the universe, does it inevitably evolve into complex, intelligent beings? On Earth, life arose over 3.5 billion years ago, but for most of that time, it consisted of nothing more than single-celled microbes. Multicellular organisms, let alone intelligent life, took an extraordinary amount of time to appear. This raises an important question. Is the evolution of intelligence a natural and inevitable process, or is it an exceedingly rare event? If intelligence is rare, then the Great Filter may lie in the evolutionary path from simple life to complex sentient beings. The long road of evolution. Earth's history provides a roadmap for how life transitions from single-celled organisms to complex, thinking creatures. This journey was not a straight line, nor was it guaranteed to happen. Many crucial steps had to take place for intelligence to emerge. The key milestones in this process include the leap from single-celled organisms to multicellular life, the development of specialized organs and nervous systems, the emergence of self-awareness and complex behavior. Each of these steps may represent a potential filter that stops life from reaching intelligence. The Great Stagnation. Billions of years without complexity. For more than 2 billion years, life on Earth remained at the microbial stage. Bacteria and archaea dominated the planet's oceans, with no signs of anything more advanced. Why did it take so long for complex life to appear? The answer may lie in the structure of cells. Simple organisms, known as prokaryotes, lack internal compartments such as a nucleus or mitochondria. These cells are small, primitive, and reproduce quickly, but they do not have the complexity needed to develop into larger organisms. At some point, a critical evolutionary leap occurred, the development of eukaryotic cells. Unlike bacteria, eukaryotic cells contain specialized structures, including mitochondria, which generate energy far more efficiently than their simpler counterparts. This energy boost allowed eukaryotic cells to grow larger and support more complex biological functions. However, this transition was not easy. Scientists believe that eukaryotic cells arose when one primitive cell engulfed another, forming a symbiotic relationship. If this event was incredibly rare, then the Great Filter might be located right here, the transition from simple prokaryotic life to complex, energy-efficient cells. If this step happens only once in a trillion cases, then even if microbial life is common, multicellular organisms may be vanishingly rare across the universe. The Cambrian explosion, a sudden leap in complexity. Once eukaryotic cells emerged, evolution proceeded at a slow pace for another billion years. Then, about 540 million years ago, something remarkable happened: the Cambrian explosion. During this period, complex animal life suddenly appeared in the fossil record. Organisms developed eyes, nervous systems, hard shells, and mobility for the first time. Within a short span of time, geologically speaking, Earth went from a world dominated by simple life to one filled with astonishing biodiversity. But why did this explosion happen? Some scientists believe that changes in Earth's environment, such as increased oxygen levels, triggered this evolutionary burst. Others suggest that a genetic breakthrough, such as the development of Hox genes, which control body structure, allowed for more complex life forms to evolve. Regardless of the cause, the Cambrian explosion shows that the leap from simple life to complex creatures was not gradual. It required specific conditions that might be rare elsewhere in the universe. If planets with simple life never experience their own Cambrian explosion, then most alien worlds might be filled with nothing more than microbes. The evolution of intelligence, a rare outcome. Even after complex animals evolved, intelligence remained exceptionally rare. Of the billions of species that have lived on Earth, only one, Homo sapiens, developed the ability to create technology, communicate abstract ideas, and contemplate the cosmos. Many animals exhibit intelligence, but very few approach human-like cognition. Dolphins and elephants have large brains and exhibit social learning, but they have not developed civilizations. Even primates, our closest relatives, have not built cities, created language, or explored the stars. This suggests that intelligence is not a guaranteed outcome of evolution. Natural selection favors survival, not necessarily higher reasoning. The development of complex brains may require highly specific conditions that rarely align. Some scientists argue that intelligence might be an evolutionary fluke, a cosmic accident rather than an inevitability. If this is true, then the great filter could be the emergence of advanced cognition itself. The role of catastrophes in shaping evolution. Another factor that may limit intelligence is the frequency of mass extinctions. Throughout Earth's history, 5 major extinction events have nearly wiped out life on the planet. The most famous, the asteroid impact that ended the dinosaurs, occurred 66 million years ago. If that event had not happened, mammals might never have taken over, and intelligent primates might never have evolved. Mass extinctions act as evolutionary reset buttons, wiping out dominant species and allowing new ones to rise. But what if Earth had suffered even more devastating catastrophes? If extinction events are too frequent, evolution may be repeatedly reset before intelligence has a chance to emerge. Planets with harsh conditions, such as frequent asteroid impacts, massive volcanic eruptions, or unstable climates, may never develop intelligent life, even if they host simple organisms. The role of cooperation and society. Even when intelligence emerges, it does not necessarily lead to technology. For intelligence to create civilizations, social structures must develop that allow knowledge to accumulate and spread across generations. Humans are unique not just because of their intelligence, but because of their ability to cooperate at large scales. Our ability to communicate, pass down knowledge, and build upon previous discoveries is what enabled the rapid rise of civilization. If alien life forms lack social structures, they may never develop advanced technology. Intelligent but solitary creatures may exist on other planets, but without cooperation they may never build radios, spacecraft, or cities. Are we the exception or the rule? So where does this leave us? There are 2 possibilities. 1, intelligence is rare. The vast majority of life-bearing planets never evolve complex thinking beings. If this is the case, then the great filter lies in the transition from simple organisms to advanced minds. 2, intelligence is common, but civilizations are short-lived. If intelligence arises frequently, then something must prevent these civilizations from surviving long enough to explore space. This would suggest that the great filter lies ahead of us, not behind us. If we are among the first intelligent species to emerge in the cosmos, then we may be at a unique moment in the universe's history, a time when life is just beginning to awaken on a galactic scale. A universe waiting to be found. The search for alien life continues, with scientists studying exoplanets, scanning the skies for signals, and exploring the possibilities of microbial life within our own solar system. But as we search, we must confront the possibility that intelligence is not the norm. It may be a rare jewel in an otherwise lifeless universe. Chapter 4: The Great Filter Ahead. Do civilizations destroy themselves? A troubling possibility. If intelligence is not the bottleneck in the universe, if civilizations emerge with some frequency, then why haven't we encountered any alien societies? The answer may be that something prevents advanced civilizations from surviving long enough to explore the stars. This is perhaps the most unsettling possibility of all, that the great filter is ahead of us, not behind. If this is true, then humanity may be on a collision course with an existential catastrophe, one that has already wiped out countless civilizations before us. What could this filter be? There are several possibilities, all of them deeply concerning. Self-destruction, the most likely culprit. One of the most widely discussed possibilities is that technological civilizations tend to self-destruct before they can become interstellar. This idea is based on the observation that as civilizations advance, they create increasingly powerful technologies that can lead to their own demise. If alien civilizations frequently develop but tend to wipe themselves out, that would explain the silence of the cosmos. The main dangers fall into several categories: nuclear war, runaway artificial intelligence, environmental collapse, biological and chemical catastrophes, uncontrollable technological progress. Each of these represents a pathway to extinction, and each one is becoming more relevant to our own civilization as we move deeper into the 21st century. The shadow of nuclear war. The discovery of nuclear weapons in the 20th century introduced a new kind of threat, one where humanity itself could become its own worst enemy. The sheer destructive power of nuclear weapons is almost unimaginable. A full-scale nuclear exchange between major powers would release enough energy to cause firestorms, mass radiation poisoning, and a nuclear winter that could render Earth uninhabitable for decades. During the Cold War, the world came dangerously close to nuclear annihilation multiple times. Even today, thousands of nuclear warheads remain on high alert. If most civilizations eventually develop weapons of mass destruction, they may also fall into geopolitical conflicts that lead to their self-destruction. Perhaps intelligent beings across the universe repeatedly reach a stage where their own rivalries, paranoia, or miscalculations cause them to annihilate themselves before they can expand into space. The AI catastrophe, losing control of intelligence. Another possibility is that civilizations create artificial intelligence far more advanced than themselves, and then lose control of it. AI systems are already becoming integral to our world, automating industries, managing financial systems, and even making decisions in warfare. But what happens when AI surpasses human intelligence? If a super-intelligent AI emerges and is not properly aligned with human values, it could lead to unintended consequences. A machine intelligence with its own goals may act in ways that are completely indifferent or even hostile to biological life. For example, a sufficiently advanced AI may seek to optimize the world according to its programming in ways that are devastating to humanity. If it is designed to maximize efficiency, it might restructure the planet's entire biosphere without concern for human survival. Perhaps in other civilizations, AI has been developed as a powerful tool, only for it to spiral out of control, leading to the complete collapse of biological life. Ecological and climate collapse. If an advanced civilization is unable to manage its resources responsibly, it might destroy its own environment before it can achieve interstellar travel. This is another lesson from Earth's own history. As human industry has expanded, so too have the dangers of climate change, pollution, and ecosystem destruction. Civilizations that rely on industrial technology may reach a point where they trigger runaway global warming, mass extinction of species, collapse of food and water supplies. If intelligent civilizations tend to prioritize short-term growth over long-term sustainability, they may burn through their planet's resources and collapse under their own weight. It is possible that advanced alien societies faced similar challenges and failed to survive. If this is true, then the Great Filter may be a test of whether a civilization can balance technological advancement with environmental stewardship. Biological and chemical catastrophes. Another path to self-destruction lies in the realm of biotechnology. As science advances, civilizations gain the ability to engineer viruses, manipulate DNA, and create artificial life. If used responsibly, these breakthroughs could eliminate disease and extend lifespans. But in the wrong hands, they could become apocalyptic weapons. A civilization that creates biological agents capable of wiping out entire populations, whether by accident or design, may quickly find itself on the brink of extinction. The same danger applies to chemical weapons and synthetic organisms. A simple laboratory mistake or an intentional act of bioterrorism could set off a chain reaction that leads to a total collapse. If civilizations frequently advance to the point where they can manipulate life itself, but fail to control these technologies, they may quickly eliminate themselves. The trap of uncontrollable technological progress. A more subtle but equally dangerous scenario is that civilizations lose control of their technological advancements in a way that renders them extinct. There is a common assumption that technological progress is always beneficial. However, if a civilization reaches a point where its inventions outrun its ability to regulate them, it may create a situation that leads to its downfall. Consider some of the risks already discussed. Automation replacing human decision-making. Weapons becoming too powerful to control. AI systems making irreversible changes to society. Environmental engineering leading to unintended disasters. If technological acceleration outpaces a civilization's ability to adapt, it may become its own undoing. Are civilizations doomed to collapse? If the Great Filter lies ahead of us, then humanity may be standing on the edge of a cosmic abyss. Every major technological breakthrough we achieve brings both promise and peril. If we navigate these challenges wisely, we may become one of the few civilizations that survive the Great Filter and expand into the stars. But if history is any indication, the risks of self-destruction are very real. If civilizations tend to reach a critical threshold where their own progress leads to their downfall, then the Fermi Paradox may have a simple and chilling answer. The universe is not silent because intelligent life never arises. It is silent because intelligent life destroys itself before it can spread. The crucial test of humanity. If the Great Filter is ahead of us, then the choices we make in the coming centuries will determine whether we pass the test or become just another civilization lost to history. We must ask ourselves, can we prevent war in an age of nuclear and AI-driven conflicts? Can we regulate technology before it outruns our ability to control it? Can we learn to live sustainably before our planet's environment collapses? If we succeed, we may be one of the first species to survive the Great Filter and explore the stars. But if we fail, we may vanish like so many before us. Chapter 5. The Dark Forest Hypothesis. Are we being watched? A universe that is not empty, but silent. The universe is vast, filled with billions of galaxies, each containing hundreds of billions of stars and planets. If intelligent life is common, then why is the cosmos so eerily silent? Could it be that alien civilizations are out there but deliberately hiding? One of the most thought-provoking explanations for the Fermi Paradox is the Dark Forest Hypothesis, which suggests that the universe is not quiet because life is absent, but because it is dangerous to reveal oneself. What if the silence of space is not a mystery but a survival strategy? The Dark Forest Analogy. The Dark Forest Hypothesis was popularized by the Chinese science fiction writer Liu Cixin in the Three-Body Problem series. It presents a chilling perspective on why advanced civilizations do not reveal themselves. Imagine a vast, dark forest. Within this forest, there are many hunters, each armed and ready to strike, but none of them make a sound. Why? Because in this forest, every hunter knows that if they reveal themselves, they risk being hunted by a stronger predator. This analogy suggests that the universe is a cosmic dark forest, where civilizations exist, but they remain hidden out of fear. Any civilization that reveals its presence might be quickly wiped out by another, more advanced one. If this is true, then intelligent species across the galaxy may have learned the same lesson. Survival depends on silence. The logic of cosmic annihilation. The dark forest hypothesis is built on several key assumptions. Resources in the universe are finite. Civilizations do not know the intentions of others. It is safer to assume that another civilization could be hostile. A civilization that reveals itself risks being eliminated. Given these factors, the safest course of action for any civilization is to remain hidden and avoid attracting attention. This concept is rooted in game theory, the mathematical study of strategic decision-making. In an environment where trust is impossible and the consequences of making the wrong move are extinction, the safest strategy is to stay quiet and eliminate threats before they eliminate you. Preemptive strikes. The first to attack wins. One of the darkest implications of this theory is that civilizations might not wait to confirm whether another species is peaceful. Instead, they may strike first to ensure their own survival. If a civilization encounters signs of another intelligent species, it might decide that the safest option is to destroy it before it can become a threat. This scenario could explain why we do not see evidence of alien life, because the moment a civilization becomes visible, it risks being targeted. Are we shouting into the darkness? If the dark forest hypothesis is true, then humanity may be making a deadly mistake. For decades, we have been broadcasting signals into space. From early radio waves to the Voyager spacecraft carrying a golden record, we have been advertising our existence to anyone who might be listening. Carl Sagan and other scientists believed that contacting extraterrestrial civilizations would be a noble endeavor. But what if it is the equivalent of lighting a fire in the middle of a dark forest, hoping that someone friendly will find us, without considering the danger? Some scientists, like Stephen Hawking, have warned against actively trying to contact alien civilizations. Hawking suggested that if we encounter an advanced extraterrestrial species, it might not be friendly. History provides a warning. When technologically advanced civilizations encountered less advanced ones on Earth, the results were often disastrous for the weaker group. If aliens exist, they may see us as insignificant or as a potential future threat to eliminate. Silent civilizations. The zoo hypothesis. An alternative but related idea is the zoo hypothesis, which suggests that extraterrestrials are aware of us but deliberately avoid contact. In this scenario, they may be treating Earth like a wildlife preserve, observing us from a distance but refusing to interfere. Why would they do this? Non-interference principle. They might follow a rule similar to Star Trek's Prime Directive, choosing not to interfere with primitive civilizations. We are not ready. They may be waiting for humanity to reach a certain level of advancement before making contact. They fear us. Even though we are less advanced, we could be unpredictable and dangerous. This could explain why we have yet to detect any signs of intelligent life, because they do not want to be found. The Fermi Paradox revisited. Is it better not to know? If the dark forest hypothesis is correct, then the silence of the universe is not a mystery, but a warning. Perhaps civilizations that stay quiet survive, while those that reveal themselves vanish. If this is true, then the best course of action might be to stop searching, or at least to stop broadcasting our presence. The challenge is that we do not know which scenario is true. The universe may be teeming with life, but if it is also filled with predators, then reaching out into space could be the greatest gamble humanity has ever made. What should humanity do? If the universe truly operates under dark forest rules, then humanity faces a difficult decision. Do we continue searching for extraterrestrial intelligence, knowing the risks? Do we stop sending signals and try to hide? Do we prepare for the possibility that we are not alone and that others may not be friendly? These questions may define the future of our species. If civilizations before us have fallen into the trap of revealing themselves, we must consider whether we are following in their footsteps. Is there a way out of the dark forest? The idea of a universe filled with silent, fearful civilizations is unsettling. But is there any hope? Some have suggested that if a civilization reaches a certain level of technological and ethical maturity, it might break the cycle. Instead of destroying potential rivals, it could create a galactic alliance, one that fosters cooperation rather than conflict. However, this would require a civilization surviving long enough to establish such a system. Enough civilizations agreeing to work together instead of competing. A way to guarantee that no rogue civilization would disrupt the peace. This is an optimistic vision of the future, but it may be a rare one. Until then, the safest option for any intelligent species may be to remain silent. Now, Chapter 6, the simulation hypothesis. Are we even in base reality? The possibility that our reality is a simulation. One of the most mind-bending ideas to emerge in recent philosophical and scientific discourse is the simulation hypothesis. Proposed by philosopher Nick Bostrom in 2003, the hypothesis suggests that it's possible, if not likely, that our reality, as we know it, is not the base reality, but instead a simulation created by an advanced civilization. The simulation hypothesis is grounded in a relatively simple thought experiment. As technology advances, particularly in the realm of computing power, it seems plausible that future civilizations could create simulations that are indistinguishable from reality. These simulations could be run for a variety of reasons: to explore history, to simulate consciousness, or simply for entertainment. The key idea here is that as technology progresses, the capacity to simulate entire universes, with conscious beings living within them, becomes more and more likely. Bostrom's argument is built on three premises. 1. It's possible for a civilization to create highly realistic simulations of conscious minds. This would require immense computing power, but given the rapid rate of technological advancement, it might be achievable at some point. 2. The probability that advanced civilizations would want to run such simulations is high. If they have the technology to create a simulation, they might do so for reasons such as research, entertainment, or historical preservation. 3. The chances that we are currently living in a simulation are significant. If it's possible for civilizations to create simulations, and if they are likely to do so, then it follows that we may be living in one of those simulations rather than in the real world. This leads to the conclusion that, given the technological trajectory of civilizations, we might not be in base reality at all. Instead, we could be part of an elaborate virtual construct designed by an advanced intelligence. The implications for the Great Filter. Now, if we accept the possibility that we are living in a simulation, it brings into question the nature of the Great Filter. The Great Filter theory argues that there's a barrier that prevents most civilizations from progressing beyond a certain point, either because they destroy themselves or because the path to greater development is exceedingly rare. But what if this filter isn't a natural or physical barrier? What if it's a programmed rule within the simulation? If we're inside a simulation, many of the existential risks or challenges we face could be artificially imposed by the creators of the simulation. In this scenario, the Great Filter could be a designed limitation, a mechanism placed in the simulation to prevent its inhabitants from breaking out of the simulated environment. This would mean that civilizations within the simulation might be destined to reach a certain level of advancement, only to encounter an obstacle that prevents them from progressing further. Perhaps the reason we haven't encountered extraterrestrial civilizations is that we are all in the same simulation, or that the simulation itself is structured in such a way that it doesn't allow for inter-simulation communication or inter-civilization contact. The filter might not be a natural occurrence at all, but an engineered limitation to maintain the integrity of the simulated reality. Are we living in a simulation? The evidence. If we entertain the idea that our reality might be a simulation, then the question becomes, what evidence do we have? While there's no definitive proof that we live in a simulated universe, there are a few arguments that suggest it might be possible. 1. The mathematical nature of reality. Our universe is governed by physical laws that can be expressed in mathematical terms. The mathematical structure of the universe, from the behavior of particles to the fabric of space-time itself, can resemble the kind of computational rules one might expect in a simulation. If the universe operates on fundamental laws that can be encoded into software or hardware, it may not be too far-fetched to imagine that it could be simulated by an advanced intelligence. Number 2, the simulation argument. Bostrom's argument suggests that if technological civilizations are likely to create many simulations, the number of simulated realities could vastly outnumber the number of base realities. If this is the case, then the probability that we are living in the base reality, as opposed to a simulated one, becomes exceedingly small. Given the vastness of potential simulations, it seems more likely that we are in one of them. 3. Technological progress. The rapid progress of technology, especially in fields like artificial intelligence, virtual reality, and quantum computing, suggests that creating a fully immersive, indistinguishable simulation might be a matter of time. As virtual worlds become more sophisticated, the idea that a future civilization could create a simulation of our entire universe becomes less speculative and more plausible. Number 4. Quantum mechanics. Some interpretations of quantum mechanics seem to suggest that reality is not as solid as it appears. The wave function collapse in quantum mechanics, where particles exist in multiple states until observed, could hint at the idea that our universe might be operating on a simulation-like algorithm, where the world only resolves into a single state when it is observed by a conscious observer. What would it mean for the search for extraterrestrial life? If we are living in a simulation, the search for extraterrestrial life could take on an entirely different dimension. The question would no longer be about finding life on other planets or across the galaxy, but rather about discovering whether other simulations exist. If other civilizations are simulated, they too might be restricted from reaching out or interacting with us. It's possible that the creators of the simulation have designed it in such a way that communication between simulations is either impossible or prohibited. In fact, the simulation hypothesis could provide an explanation for the Fermi Paradox. Perhaps advanced extraterrestrial civilizations exist, but they are simply in different simulations or even programmed to not engage with us. If we are all part of separate, isolated simulations, then the universe may be far more populated than we think, but we are unable to make contact because of the structural limitations of our simulated reality. Additionally, the notion of a simulated universe could have profound implications on the way we search for extraterrestrial life. Rather than focusing on biological life forms and traditional space exploration, we might instead need to explore the idea of simulation detection, looking for inconsistencies or glitches in the fabric of reality that might reveal the underlying artificiality of our world. The consequences of the simulation hypothesis. The implications of living in a simulation would be far-reaching. If our reality is a simulation, it would raise fundamental questions about the nature of consciousness, free will, and existence itself. Are we truly conscious beings with free will, or are we simply programmed responses to environmental stimuli, part of a grand experiment orchestrated by entities beyond our comprehension? Could we, as conscious beings, ever break out of this simulation, or are we bound by the limits of our programmed existence? Moreover, if we are in a simulation, the search for extraterrestrial life may be an exercise in futility. After all, if we cannot even verify the nature of our own reality, how can we expect to detect life beyond it? The true question becomes, can we ever escape the simulation, or are we fated to remain within it forever? Chapter 7: Escaping the Great Filter: How Humanity Can Survive. Space colonization and the need for multiplanetary survival. The Great Filter theory postulates that the rise of intelligent civilizations is extraordinarily rare, with the vast majority failing to surpass one or more key filters. One of the most crucial filters could be self-destruction, whether through warfare, environmental collapse, or resource depletion. Given the fragility of life on Earth, the most effective strategy to ensure the long-term survival of humanity may be to escape the gravitational pull of our home planet and establish human colonies on other planets. Space colonization is not just a luxury or a futuristic dream. It is an imperative for the survival of our species. The idea is to spread humanity across different planets and moons, ideally across different star systems, to create a multi-planetary civilization. This approach significantly reduces the risks posed by planetary-scale disasters like asteroid impacts, climate change, nuclear war, or other global catastrophic events. In recent years, there has been significant progress toward making space travel and colonization a reality. Various organizations and space agencies around the world are working on spacecraft technologies, including the development of reusable spacecraft, designed to carry large numbers of people to Mars and other destinations in the solar system. However, space colonization is not without its challenges. Terraforming planets to make them habitable, providing long-term life support systems, and creating sustainable ecosystems on other planets are all monumental hurdles. Yet, the potential rewards are equally extraordinary. By establishing colonies on different planets, humanity could dramatically increase its chances of surviving the Great Filter. If one planet or colony fails, others may remain viable, ensuring the continuation of human civilization. Beyond Mars, other celestial bodies such as the Moon, Europa, a moon of Jupiter, and even Titan, a moon of Saturn, are prime candidates for colonization. These locations may offer the resources, including water and minerals, needed to sustain life. Space colonization could be the ultimate way for humanity to escape the looming threat of extinction and create a safety net for the survival of our species. The role of AI, biotechnology, and futuristic solutions. To escape the Great Filter, humanity will need to leverage cutting-edge technologies to overcome the challenges of colonization, resource scarcity, and existential risks. Artificial intelligence and biotechnology will play central roles in these efforts. AI, the path to autonomous exploration and survival. AI has the potential to revolutionize space exploration and colonization. With the ability to process vast amounts of data and make decisions at speeds far beyond human capabilities, AI could be instrumental in designing autonomous spacecraft and robots that can handle the harsh conditions of space travel and planet colonization. These AI systems could be used for automated resource extraction. AI-driven robots could mine asteroids or planets for vital materials such as water, metals, and rare elements. Terraforming efforts. AI could optimize and monitor large-scale terraforming projects, such as adjusting the atmosphere or creating sustainable ecosystems. Life support management. AI systems could be designed to monitor and maintain life support systems in extraterrestrial habitats, ensuring that colonies remain viable for long periods without human intervention. By combining AI with machine learning and deep space communication technologies, we could enable the exploration of distant star systems in ways that were previously unthinkable. AI's potential to assist with critical tasks such as resource management, environmental monitoring, and autonomous decision-making makes it a vital tool for humanity's escape from the Great Filter. Biotechnology, engineering life for space. Another critical area in overcoming the Great Filter is the development of biotechnology. As we venture beyond Earth, human biology will face significant challenges. The lack of a protective atmosphere, exposure to high levels of radiation, and the psychological effects of long-duration space travel could be detrimental to human health and survival. Biotechnology can provide innovative solutions to these challenges. Genetic engineering. Modifying the human genome to enhance resilience to space travel's effects, such as radiation resistance or bone density preservation, could be essential for long-term space colonization. Scientists are already exploring genetic modifications that might enable humans to thrive in low-gravity environments. Synthetic biology. By designing and creating artificial life forms, we could engineer microorganisms to produce food, oxygen, or even help with waste management on distant planets, reducing the dependency on Earth-based resources. Bioreactors and closed-loop ecosystems. Advances in biotechnology could lead to the development of self-sustaining ecosystems, where organisms are genetically engineered to recycle waste, purify water, and provide food, creating a closed-loop system necessary for long-term survival in space. Biotechnology holds immense potential for enhancing humanity's chances of survival and thriving on planets that are far from the Earth's natural resources. Futuristic solutions. The power of energy and advanced materials. To truly escape the Great Filter and establish a sustainable multi-planetary civilization, we will need to develop futuristic energy solutions and advanced materials. A key area in this regard is the energy challenge. To support life on other planets, we will need to harness energy in a way that is efficient, scalable, and capable of supporting the technological infrastructure required for space colonization. Nuclear fusion. The development of nuclear fusion as a clean, virtually limitless energy source could provide the necessary power to sustain human colonies on other planets. Fusion energy would offer abundant, non-polluting power for everything from space travel to life support systems. Solar power and space-based energy generation. Solar power will continue to be crucial, especially in space environments where sunlight is abundant. We could build massive solar arrays in space, where solar energy can be collected and transmitted to colonies on other planets or moons. Advanced materials. To withstand the harsh conditions of space, we will need materials that are lighter, stronger, and more adaptable than anything currently available. Nanotechnology and the development of graphene and other advanced materials will play a crucial role in building spacecraft, habitats, and life support systems that can endure the extreme conditions of space and distant planets. These futuristic solutions, when combined with AI and biotechnology, could give humanity the tools needed to thrive in space and beyond. What it would take to become a Kardashev Type 1, 2, or 3 civilization. In the quest to escape the Great Filter and ensure humanity's survival, we must also consider the idea of becoming a Kardashev Type 1 civilization and beyond. The Kardashev scale is a theoretical framework proposed by Russian astrophysicist Nikolai Kardashev in 1964 to classify civilizations based on their energy consumption. Type 1 civilization. A civilization that can harness and use all the available energy on its home planet. This includes mastering all forms of energy, such as geothermal, wind, solar, nuclear, and fossil fuels, in a sustainable way. Achieving Type 1 status would be a monumental milestone for humanity, signifying that we have the ability to manage our planet's resources effectively and avoid self-destruction. As of now, humanity is estimated to be at 0.72 on the Kardashev scale, meaning we still rely heavily on fossil fuels and have yet to tap into the full potential of renewable energy. Type 2 civilization. A civilization that can harness and control the energy output of an entire star. This would involve building mega-scale structures, such as a Dyson sphere, a hypothetical structure that could encompass a star to capture its energy output. Type 2 civilizations would likely have interstellar travel capabilities and could colonize other star systems, ensuring their survival even if their home planet faces existential threats. Type 3 civilization. A civilization that can control the energy output of an entire galaxy. Achieving Type 3 status would mean that humanity has the ability to travel between stars, harnessing the energy of multiple suns and colonizing many planets across the galaxy. Type 3 civilizations would likely have technologies that are far beyond anything we can currently imagine. For humanity to escape the Great Filter, we must aim for Type 1 status first, as a stepping stone toward the higher levels of the Kardashev scale. This would involve transitioning to sustainable energy sources, mastering space colonization, and advancing technology to a level where we can ensure the long-term survival of our species.